Voltage, vitality, elevation.
When we imagine the universe, we imagine abundance. Stars packed into galaxies, galaxies packed into clusters, light everywhere. But this picture is wrong. On the largest scales known to science, matter is not dominant. It is not even common. In fact, almost everything we have ever observed, every star or planet, every living thing, occupies only a thin fraction of cosmic real estate. The universe is not defined by what it contains. It is defined by what it does not. Welcome to the realm of intergalactic voids, the vast expanding regions of near-nothingness that shape the universe itself. As astronomers began mapping the universe in 3 dimensions during the late 20th century, a startling pattern emerged. Galaxies were not scattered randomly through space. Instead, they traced long, interconnected filaments, immense bridges of matter stretching across hundreds of millions of light-years. At the intersections of these filaments lie galaxy clusters, gravitational giants containing thousands of galaxies and enormous reservoirs of dark matter. These luminous nodes form the bright skeleton of the universe, but the skeleton is not the body. Surrounding these filaments are vast regions where galaxies are scarce or entirely absent. These are not gaps between structures, they are the structure. This network of filaments, sheets, clusters, and empty regions is known as the cosmic web, and it is dominated not by matter, but by voids. More than 80% of the observable universe's volume lies inside these immense regions of emptiness. An intergalactic void is a region of space where the density of matter is dramatically lower than the cosmic average. In these regions, galaxies are rare, often separated by tens of millions of light-years. Gas is diffuse. Dark matter exists only in faint, thread-like filaments too weak to collapse into large structures. Voids are not completely empty, but compared to the rest of the universe, they are profoundly underpopulated. They range in size from tens of millions to hundreds of millions of light-years across, dwarfing even the largest galaxy clusters. Some voids merge with others, forming colossal supervoids that span significant fractions of the observable universe. Far from being static, voids evolve, expanding, merging, and reshaping the cosmic web over billions of years. Voids were not discovered by accident. They revealed themselves through absence. As astronomers conducted redshift surveys, measuring how fast galaxies recede due to cosmic expansion, they noticed enormous regions where galaxies simply failed to appear. These gaps were too large and too structured to be random. In 1987, astronomers R. Brent Tully and Richard Fisher identified one such region near our own cosmic neighborhood. This structure became known as the local void, a massive underdensity adjacent to the local group of galaxies, which includes the Milky Way. The local void extends at least 150 million light-years, possibly more, and is partially hidden behind the dust and stars of our own galaxy. To see into it, astronomers turn to radio telescopes, using the 21-centimeter emission of neutral hydrogen, a wavelength capable of penetrating galactic dust. Observations from instruments such as Arecibo, the Green Bank Telescope, and Meerkat confirmed what optical surveys suggested. We live on the edge of a vast cosmic emptiness. You cannot photograph a void directly. Instead, astronomers map voids by observing motion. Galaxies move not only with cosmic expansion, but also with additional velocities caused by gravitational forces. These deviations, called peculiar velocities, reveal where mass is present and where it is missing. Using massive datasets such as cosmic flows, astronomers track the motions of tens of thousands of galaxies. When these motions are visualized, a striking pattern appears. Galaxies flow away from voids. This process, known as void evacuation, occurs because matter drains from underdense regions toward denser filaments and clusters. Over time, voids expand faster than the universe as a whole. In cosmology, emptiness is not passive, it drives motion. The existence of voids is a direct prediction of the lambda cold dark matter model, or LCDM, the standard model of cosmology. According to LCDM, 5% of the universe is ordinary matter, 27% is cold dark matter, 68% is dark energy. Dark matter collapsed first, forming an invisible framework of filaments and nodes. Ordinary matter followed, cooling and forming galaxies along this scaffold. But gravity amplifies asymmetry. Slightly underdense regions lose matter, while overdense regions gain it. Over billions of years, this process carves the universe into dense structures surrounded by expanding voids. In LCDM, voids are not optional, they are inevitable. The true origin of voids lies in the first fractions of a second after the Big Bang, during a period known as cosmic inflation. During inflation, space-time expanded exponentially, stretching tiny quantum fluctuations to cosmic scales. These fluctuations produced minute variations in density, differences of just 1 part in 100,000. Some regions began slightly denser, others slightly emptier. Over 13.8 billion years, gravity amplified these tiny differences. Dense regions became galaxies and clusters. Empty regions became voids. Voids are therefore fossils of the universe's earliest moments, preserving information from energies far beyond the reach of any experiment on Earth. In slow-roll inflation, the inflaton field descends gently along a potential energy landscape, producing nearly Gaussian scale-invariant fluctuations. In this scenario, voids arise from the negative tail of a random distribution. Statistically inevitable and predictable, but more exotic models exist. In eternal inflation, quantum fluctuations cause inflation to continue indefinitely in some regions, creating a multiverse of bubble universes. Our observable universe may be just one such bubble, with voids reflecting deeper randomness in inflationary physics. More complex models predict non-Gaussianity, correlations between fluctuations that increase the likelihood of extreme underdensities. Voids are exceptionally sensitive to these effects, making them powerful probes of early universe physics. Void statistics, including size distributions, density profiles, and topology, are now used to test inflationary models with extraordinary precision. Voids are also crucial to understanding dark energy, the force driving the accelerating expansion of the universe. In low-density regions, dark energy dominates earlier and more strongly. Voids expand faster than average, amplifying the effects of cosmic acceleration. Some theories of modified gravity predict deviations that appear most clearly inside voids, making them ideal laboratories for testing fundamental physics. As time goes on, voids will grow larger and emptier. Galaxies will retreat into isolated islands, separated by ever-expanding darkness. The long-term fate of the universe belongs not to matter, but to emptiness. Long before galaxies formed, before stars ignited, before voids became vast expanses of near-nothingness, the universe left behind a faint but powerful signal, the cosmic microwave background, or CMB. This radiation is the afterglow of the Big Bang, released when the universe was just 380,000 years old. It is remarkably uniform, yet imprinted with tiny temperature fluctuations that mirror the density variations created during inflation. Intergalactic voids leave subtle fingerprints on this ancient light. As CMB photons pass through large voids, they experience a phenomenon known as the integrated Sachs-Wolf effect. In an accelerating universe dominated by dark energy, gravitational potentials decay over time. When photons enter a void, they lose energy climbing out, but they do not fully regain it. The result is a slight cooling of the CMB in the direction of large voids. Some of the largest known supervoids appear spatially correlated with cold regions in the CMB, including the mysterious cold spot in the southern hemisphere of the microwave sky. While the connection remains debated, it raises a profound possibility that the largest empty regions in the universe may still be influencing light that has traveled for nearly 14 billion years. Nothing, it seems, leaves an imprint. Modern cosmology no longer treats voids as curiosities. They are now measured with precision. Using massive galaxy surveys, including the Sloan Digital Sky Survey, DESI, and Euclid, astronomers construct detailed void catalogs, identifying thousands of voids across cosmic time. Each void is characterized by radius and volume density contrast shape and ellipticity surrounding compensation walls. The void size function, the number of voids at each scale, is particularly sensitive to cosmological parameters. Even small deviations from LCDM predictions would alter the abundance of large voids. Unlike galaxy clusters, voids are minimally affected by complex baryonic physics, such as star formation and feedback. This makes them among the cleanest probes of fundamental cosmology available. In a universe filled with noise, voids are clarity. General relativity has passed every major test within the solar system and on astrophysical scales. But on the largest scales of all, questions remain. Some theories propose that gravity itself may behave differently in low-density environments, particularly inside voids. These theories include scalar tensor gravity, FR gravity, and chameleon screening mechanisms. In dense regions, deviations from general relativity are suppressed. But inside voids, where matter density is extremely low, alternative gravitational effects could emerge. This makes voids a unique testing ground, regions where gravity is weakest and therefore easiest to challenge. So far, observations remain consistent with Einstein's theory. But the fact that voids are among the best places to look tells us something important. If gravity ever breaks, it will break first in the emptiest places. The study of intergalactic voids is entering a new era. Upcoming missions such as Euclid, the Vera C. Rubin Observatory, the Nancy Grace Roman Space Telescope will map the universe with unprecedented depth and precision, identifying millions of galaxies and tens of thousands of voids. These surveys will allow cosmologists to track void evolution across cosmic time, measure dark energy's influence with higher accuracy, test inflationary physics at previously inaccessible scales. Voids are transitioning from passive features to precision instruments, tools for probing the deepest laws of nature. The universe's emptiest regions may hold its most important answers. There is a deep irony at the heart of cosmology. The brightest objects in the universe, stars, galaxies, quasars, live short, violent lives. They collide, explode, and erase the very history that created them. But voids endure. They evolve slowly. They remember their origins. They preserve information from the earliest moments of time. The universe speaks most clearly not where it is loud, but where it is quiet. As the cosmos continues to expand, voids will grow larger, colder, and more dominant. Galaxies will fade beyond each other's reach, and the universe will become a scattered archipelago of light surrounded by infinite darkness. The grand scale of the universe isn't built from galaxies and stars alone. It's built from the spaces between them, from vast intergalactic voids, born from quantum ripples, stretched by inflation, and carved by gravity over billions of years. These aren't empty mistakes, they're the blueprint. Galaxies exist because of matter gathered in some places, and left others silent. These voids will grow and quietly preserve the memory of how everything began. Because in the end, the universe isn't defined by what's there, but by what isn't. Thanks so much for watching. Zap the like button and subscribe for future uploads to the channel so you don't miss a thing. Stay curious, guys, and always stay elevated.
Thanks for watching Voltage Vitality Elevation. Please select one of the videos displayed on the screen to continue watching.